Alrighty, let's get started for today. So I was looking over the calendar to see how many class periods we have left before the end of the semester and stuff like that. And I've decided the best thing to do, because the plan is to have this topic, which is fluids, and have a test. And then one more topic, which is optics, light and optics, and then have a test on that. And then we'll have the final exam. Well, given that we basically have 1 month left of classes before final exam week starts, in order to be able to get through this stuff and still have, time to go over the material, I'm going to be cutting the topic of fluids a little short. Basically, fluids I break up into kind of two halves. The first being the Bernoulli stuff, and the second being Archimedes' principle. And I think the best thing to do is just focus on the Bernoulli stuff for now, and then have a test on it. And then we can start into light and optics. That way, I'm able to give you some information about optics, and you have kind of a more general overview of a bunch of different topics by the time we get to the end of the semester. So because of that, here's kind of the little bit of a layout of what's going on. Today, we will work on examples and such for the material we've already done, which is, of course, Bernoulli's principle, but also the pressure depth relationship that we did last time, or we introduced it last time. Thursday, we will do an exam review. And then Tuesday of next week will be exam 2, which will be on fluids. And then Thursday of the following week is when we'll start into optics, do about 3 or 4 class periods on optics, and then we'll have an exam review for that, exam 3 on optics, and then we'll still have time to do a final exam review day before final exam week happens. So that's what we're looking at for the coming week, is finish up fluids today, the stuff we've been doing, work some example problems. Thursday, we'll have an exam review, which basically means I'll go over the topics we discussed, give you a chance to ask me any last minute questions on any of the topics and the like. And then on that Tuesday, we will have the test for fluids. So with that said, we could go ahead and look into finishing up these example problems. Last time, we introduced what's called the pressure depth relationship. And basically what this is an equation, a way to predict how much pressure you would expect an object to feel because they are inside of a fluid. Okay. But it turns out that the deeper you go, the more pressure you feel. Now, why might that be? Well, imagine there's, water, and you go down in the water, and here's an object inside, under the water, submerged in the water. Well, first thing you need to understand is that in order for the object to be in the water like this, well, it wasn't there before, and then you place the object in the water. Well, now, whatever water was there where the object is currently located had to move out of the way to make room for the object. Because originally you just had a body of water. Now you place an object in it. Well, the object is taking up room where water was originally. So that water had to move out the way for this object to be there. So naturally, the water wants to go back to where it was. And so in all directions, the water is trying to go back to where it was when it was moved out of the way. And this, of course, makes a pressure. The water is trying to force its way back. The object's there, so the water is pushing against the object. And so you get a pressure acting on this object in all directions. Well, because of that, what we can see is all the pressure coming from the left side, let's say, must be balanced by the pressure coming from the right side, right? There's a bunch of water trying to move in from the left. There's a bunch of water moving from the right. And so left to right, these kind of balance out. However, up and down, what you have is the amount of, you can imagine it like this. If there's an object under the water, then there's like this column of water above it, which is basically sitting on top of the object. Well, if you imagine you're in air and there's like a stack of books on top of you, well, the higher the stack of books, the heavier it is. And so the more weight is pushing down on you, thus the more pressure you feel. Well, the same thing here. When an object is underwater, the amount of water above it, which is pushing down, because of course gravity is trying to pull everything down, whether it's water molecules or box molecules, it doesn't matter. And so there's gravity trying to pull this fluid down, or this water in this case. And the more water you feel, so the deeper the object is, let's say, the bigger the column of water that's above it, and thus the heavier that amount of water is. The heavier it is, the more force the object feels. The more force it feels, the more pressure it feels. And so that's why there's a relationship between the pressure felt by an object and the depth of that object. The deeper you go, the more water there is on top of you pushing down on you. That's one kind of way of thinking about why this is. Well, of course, what is the relationship? What is the actual mathematical equation? Very easy. The pressure is going to be rho times G times H. Okay, where rho, that's the density of the fluid. So of course, this should depend on what kind of fluid you're in. If you're in air, then air is not so heavy, so you shouldn't feel that much pressure. Whereas if you're in water, the water is more dense. Because it's more dense, it's more heavy, and thus you would expect to feel a larger force, a larger pressure. So first thing this should depend on is what kind of fluid are we talking about? Is it a very dense fluid? Then you'd feel more pressure. It is a very light fluid, you should feel less pressure. G, of course, is the standard acceleration due to gravity here on Earth, 9.8, the same number we always use. And H is the variable for the depth. The deeper you are, the more fluid is on top of you pushing down, and thus the higher the pressure you should feel. So there's the pressure depth relationship. And of course, we also said that there's a distinction we have to make when we're discussing these issues, when we're working some of these problems, between how much pressure an object feels and how much more pressure it feels, particularly because of its depth. All right, these are two different questions, because obviously what we know is if an object is just sitting on the surface, so let's say we have an object just sitting on top of the water right here, not under the water yet, well, that object is at zero depth, right? It's not actually submerged into water yet, so there's no water above it to push down, and thus you should expect not to feel any pressure. However, the object actually is in a fluid, it's just not the water, it's actually in the air. And the air, being a gas, is a fluid. And so the air itself should also be applying a force to the object. It's just that we don't notice it because everything in the world, everything on Earth feels this pressure. Everything is in the air, and thus everything feels this pressure all the time. Now, obviously, in a more realistic setting, we understand that the amount of pressure an object feels in the air depends on where it is. Is it up on a mountain where the air is thinner and thus you should feel less pressure, versus are you at sea level where you're, at the deepest point, let's say, or in New Orleans where you're a little below sea level and the air is at its thickest or most dense, and so you should feel more pressure because the air is more dense there. So yes, there's a difference in pressure depending on how high up you go or how low you go, but just for our purposes, introducing this stuff, we say that an object feels standard atmospheric pressure. So atmospheric pressure is simply the amount of pressure an object feels because it's in the atmosphere. It's in air on Earth. Now, I'll go ahead and use the symbol PATM. And it turns out to just be a constant. Like I said, this is an average number because it does depend on how high, what your altitude is. But we'll use for our purposes 1.01 times 10 to the 5th pascals. Okay. So we automatically say every object, even if it's not underwater yet, already feels atmospheric pressure. And so if this is true, then when an object does get submerged in water, first of all, it still feels this atmospheric pressure. Everything feels it. So it's already got that, but then it also feels the effects of the fact that it's now underneath a different fluid, this being water, let's say. And so that's where the difference comes in between what's called the gauge pressure and the absolute pressure. Okay. The gauge pressure is simply how much pressure does it feel different than what it is naturally. So the, how should I say it? Let's say the new pressure or the excess pressure. So not the total pressure, it's just, it was at atmospheric, now it feels this more in excess pressure because it's at some depth. Absolute pressure is the total pressure. Everything included.
So for gauge pressure, you just need the first equation. You just need pro gravity times depth. For absolute pressure, you take that equation, you just add it, and you add 1.01 times 10 to the fifth pascals.
That's exactly right. Yeah.
Okay.
Gauge pressure, this equation, what we have here, the actual pressure depth relationship as it's written, must be gauge pressure. And the way we can see it is, well, assume the object is at 0 depth. So it's on top of the water. So we place H is equal to 0. Well, obviously that makes the pressure 0. But we know that an object on the surface of the water is not at it's not at 0 pressure. It's at least at atmospheric. So the fact that this equation does not take that into account tells us this must be a gauge pressure equation. And so just as you said, well, then how in the world do we calculate absolute pressure? It's very easy. Absolute pressure is nothing more than the gauge pressure plus atmospheric. Okay, so this is something that must be kept track of when you're doing actual work, depending on what is important. If you're doing scientific work and you need to know exactly how much pressure an object's going to feel, then you better take into account atmospheric pressure along with whatever you're doing to change it. However, if you're a scuba diver, or let's say you're pumping up a bicycle tire. Well, the fact that the bicycle tire, when it's empty, is already at atmospheric pressure doesn't help, because who cares? It's empty, it's flat. The atmospheric pressure isn't helping it to be more than flat. That is the flat state. So you don't care about the atmospheric pressure. What you care about is how much more you've pumped up the tire than its flat, normal, standard state. And so in those or if you're, like I said, a scuba diver going under the water, well, you don't really care about atmospheric pressure because that's your 0 point. You care about how much more pressure you're about to feel. And thus the instruments on your belt or whatever stuff you're taking down with you really will only tell you about how much extra pressure it feels. And so the 0 pressure is atmospheric pressure. So it depends, when do you use gauge pressure? When do you use absolute pressure or total pressure? Well, it depends on the purposes that we're talking about. How will you tell for this class? That's an even more important question. And the rule I use for the classes we're doing is unless I state specifically otherwise, you're going to be talking about gauge pressure. So if I say a diver dives 10 meters under the surface of a freshwater lake, what pressure will he feel? That you're going to assume I mean the gauge pressure. Now, how will you know if I mean absolute pressure? I'll say it specifically. I'll ask, what's the absolute pressure this person will feel? Or what's the total pressure felt by this person? Then you know, okay, he means absolute pressure. If I don't say either absolute pressure or total pressure, then just go ahead and assume I mean just the gauge pressure, and so you just do the rho GH calculation. Okay, that's the rule we're going to use. That's not the rule for everybody. That's not standard in the industry. So when you leave my class, just keep that into account. You better understand the rules or what's going on with whatever you're working with there. But for us, just so that we're clear about it, so there's no confusion on a test or something, the rule is it's gauge pressure unless I say specifically, give me the total or the absolute pressure. And also remember this equation that I have written right here, you can either write it that way, or you could say gauge pressure is absolute pressure minus atmospheric. Okay, so, every equation I ever write in physics, and this is just a rule to understand about physics in general, engineering, mathematics, chemistry, anything. Whenever an equation is written, just because the equation says something equals something else, that doesn't mean the equation is purely for that first thing. So in this case, absolute pressure is gauge plus atmospheric. That doesn't mean this equation is only for absolute pressure. So if I ask for gauge pressure, you can't use it. Well, that's obviously not true. You're now at a point where you're sophisticated enough mathematically to take one equation and create all these other equations out of it just by manipulating it. So I can move this equation around to create that equation. And so now I have an equation for gauge pressure if I happen to know what the absolute pressure is. Okay? This is a general rule, and it's true of all equations in physics. Anytime I give you an equation, like let's say we have the, x equals v naught t plus 1/2 at squared, our old kinematics equation. Well, just because I write it like this doesn't mean the only thing you could solve for is position. You could solve for initial velocity if you want, or acceleration, or time. It doesn't matter. All of these variables can be solved for using this one equation. And so the same thing with what I have written here with the gauge pressure and absolute. Just understand that this equation can be used to solve either the gauge pressure or absolute, depending on which you have. Okay. Now, I say that because I have a bunch of experience teaching these classes and giving tests and stuff. And I've seen people where let's say I've given them the gauge pressure version, I've given them this version over here. And then on the test, I asked them to calculate the absolute pressure and they didn't know how to do it. Well, just take this gauge pressure equation and solve for absolute pressure. That's all you got to do. Just move it around and you have the other one. So just know for the future and generally speaking in the scientific courses that this is expected of you. Given an equation, I have to write it somehow. So we usually solve it for one particular variable. Just know that that equation can be used to solve for any of the variables. All right. So that's the pressure depth relationship. So what is a typical kind of example or a problem you might see? Well, it goes something like this. A solid sphere is submerged in honey at a depth of 3 meters. Calculate the gauge and absolute pressures felt by the sphere. And of course, you need one particular piece of information, which will say the density of honey will be set to, let's say, 2,000 kilograms per cubic meter. Okay. And so what do we have? Well, we basically have, here's our thing of honey. We have some kind of a vat. And we have our object, a sphere, is placed a distance 3 meters below the surface. And we want to know both pressures, the gauge pressure and the absolute pressure. All right, well, that's no big deal. The gauge pressure, we could use the straight up formula. Pressure is rho times G times H. And then all we need, the density of the fluid, well, in this case, we're talking about honey, and I'm told the density of honey is 2,000 times G, that's 9.8, times the depth we're at, which is 3 meters. So pretty straightforward. We have all of our numbers. We just plug them in our calculator and we'll get our answer. And what we get is 58,800 pascals. Or if you like scientific notation, 58.8. I'm sorry, what am I doing? That's not standard. 5.88 times 10 to the 1, 2, 3, 4th pascals. Okay, so that's how much extra pressure this solid sphere will feel because it's under the honey. It's under the surface of honey. Now, part B, the absolute pressure. Well, once we know the gauge pressure, this is really easy. Absolute pressure is just the gauge pressure plus the atmospheric pressure. So gauge pressure, 5.88 times 10 to the 4th, plus atmospheric, 1.01 times 10 to the 5th. And we'll get our answer. We get 1.598, let's say, times 10 to the 5th pascals. So obviously more than atmospheric because it's already got atmospheric, then it also goes underneath the honey. So it's going to feel more pressure than it was before. And thus we have about 1.6 pascals, let's say. All right, so any questions about this particular example?
So I may have asked about this
Yeah.
like last time, but I just wanted to make this clear. So your pro in this case, or your density is kilograms over meters cubed. And then the gravity is going to be in meters per second squared, right? And then the density, not density, that's going to be in meters. So that would give us, I believe, kilograms per meter second squared, and that's the unit for pascals, the actual unit.
Yeah, let's see. Let's actually go through it. That'll be a fun little exercise. It's always good to do to make sure. So looking at this equation right here, pressure, which I'm claiming is pascals, is density, which is kilograms per meter cubed, times gravity, which is meters per second squared, times height, which is meters. So that's kilograms times meters squared per meters cubed seconds squared. So these meters squared cancel those, and we get kilograms per meter second squared. Now, that's weird. Weird units, and I'm claiming that's pascals. Well, let's make sure that's actually pascals, because I know a second equation for pressure. Pressure, if you remember, was defined to be the force felt divided by the area. How much force is applied over what area? And I know force is newtons and area is meters squared. Newtons, if you remember, force is mass times acceleration. So newtons is kilograms meters per second squared over meters squared. So this meters cancels one of those meters, and we get kilograms per meters second squared. Indeed, exactly the same units. So yes, pascals, officially the units are kilograms per meter second squared, which are the same as Newton per meter squared. And that's what we call a pascal. So we don't have to keep writing that. But yeah, that's exactly what the units are. Perfect.
All right.
Any other questions? So this particular calculation is pretty straightforward. There's not really any tricks I can do. The units, I mean, unless I give you a depth that's not in meters, the units are always fine. There's nothing really I could, make complicated here. All you have is what is the fluid, so the density of the fluid, and that's usually given to you in the problem. G will always have 9.8. We're not going to be on a different planet. And the depth, well, I have to tell you how deep. And so I give you some depth. Of course, make sure it's in meters, but it usually is. So really the only place where a mistake can be made, relatively speaking, is knowing the difference between gauge pressure and absolute pressure. Absolute means the total pressure. It's how much are you normally at, which is atmospheric, plus the extra bit, which is called the gauge pressure. And so usually it's best, if you want to calculate the total pressure, you first calculate the gauge pressure, and then you just add in atmospheric to it. So there's not really too much we could do with this, this particular type of calculation. All the examples are exactly identical to this. All I can do is change up what kind of fluid are we talking about and how deep is it. The shape of the object doesn't matter. The size of the object doesn't matter. None of that matters. It's purely what is its depth and what is it in, and that's all there is to it. So because of that, what I did want to do is do a couple more examples with Bernoulli, because I think Bernoulli is a little bit more complicated, or can be more complicated than this. So I'll go ahead and work a couple more Bernoulli problems to make sure we get that, especially since we're going to be having the test coming up. So we'll have another example of Bernoulli. Let's say we have a question like this. A pipe diameter 1 meter has water flowing at a speed of 5 meters per second. The pipe runs along for 20 meters, where it bends upwards and rises to a height of, let's say, 30 meters. From there, the pipe bends back straight and runs for another 15 meters. At this point, it let's say it constricts to a radius of, let's say, 10 centimeters. Calculate the difference in pressure between the two ends. All right. So there is our pipe system. We have a pipe, certain size, water flowing through it at a certain speed. The pipe runs along, bends upwards, goes up to a new height, and then straightens back out again, and then runs along again, and then it changes size. And we want to know what's the difference in pressure. So definitely a Bernoulli problem, pipe system, fluid flowing through the pipe, and the pipe changes size and whatnot. And you want to know about the pressure. That tells you Bernoulli. Now, before we calculate anything, let me go ahead and draw this out so we can see what we're working with. It's easier if we can visualize it. What we have is a pipe, looks like this. So here's the initial pipe. First of all, we know the diameter, D1, is 1 meter. And we have fluid flowing through with a velocity V1 of 5. And we're told the pipe runs along for 20 meters. So goes along for 20 meters. So from here to here, 20 meters. And then it bends upwards and goes to a new height. So there's the bend. And it rises to a new height of 30. So now from here to here is 30 meters. Okay. From there, the pipe bends back straight and runs for another 15 meters. So now it runs for 15 meters. So from here to here is 15 meters. At this point, it constricts to a new radius of 10. So it gets smaller. There we go. And we're told the radius here, R2, is 10 centimeters. Well, we know centimeters is bad, so let's go ahead and convert now. That's 0.1 meters. And I want to know the difference in pressure between the original point and the end point. All right, so that's what our pipe system looks like if I were to draw it out. And this is something you should be able to do. You should be able to read through the problem, if it's just a word problem, and sketch out what the pipe should look like purely from the words. Of course, you should also be able to do the problem if all you have is the picture and you don't have the words. You should be able to look at this picture and understand what are all the pieces of information, what do they all mean, and then be able to calculate from there. So there it is, the words and then the pictures associated with those words. Now, how do we actually solve the problem? Well, being a Bernoulli problem, we know Bernoulli's equation, P1 plus rho GH1 plus 1/2 rho V1 squared plus P2 plus rho GH2 plus 1/2 rho V2 squared. All right, so that's Bernoulli. The first thing I usually do is I see, are there any terms we could cancel out? Because if we could cancel any of these terms out, it'll make the calculation easier. There's less stuff to have to add and subtract. And the way I see it is I say, okay, firstly, does the height change? Because if it doesn't change height, then the rho GH terms can just cancel out. Well, unfortunately, it does change height, so I have to keep the height terms. It goes up by 30 meters, thus I need to keep those terms. Second thing I ask is, does it change velocity? How do I know if it changes velocity? Does it change size? If the size of the pipe changes, then the velocity will change. So I look at the two ends and I say, do they have the same size? Well, initially, I'm at a diameter of 1 meter, and at the end, I have a radius of 0.1 meters. Well, I already don't like this diameter business. Diameter is bad because I know that eventually, when I go to calculate the speed, I need area, and area uses radius. So first thing I'm going to do is just, instead of having diameter there, I'm going to convert it to radius, and I know that the radius of the pipe is just the diameter divided by 2. So really R1 is 50 centimeters, which is 0.5 meters. Okay. So the question is, does it change size? Well, yeah, initially it's got a radius of 0.5, and at the end it's got a radius of 0.1. So the size does change. Thus, unfortunately, we cannot cancel out the terms with speed, with velocity. So I need to keep all the terms. All right, well, that's the way it is. We have to keep all the terms. However, I do know what it is I'm looking for is the difference in pressure. So what that means is difference in pressure is P2 minus P1. So I want to take my Bernoulli equation, rearrange some of the terms so that one side of the equation has P2 minus P1, and the other side has everything else. So that's what I'm going to do. Here's my equation. P2 is over here already, so I want to put P1 on the other side. Of course, when I do that, it becomes negative. I'm moving it to the other side of the equation. It changes sign. So I have P2 minus P1. The problem is all of this stuff over here is over there with P2 minus P1, and I don't like that. So I have to move them over as well. So I'm going to move these two terms over to the other side. And of course, when I do that, they also get negative signs because they change sign when they go over to the other side. So now what's on that side of the equation? Well, rho GH1 is there. And now I've moved rho GH2. So he's minus rho GH2. 1/2 rho V1 squared is there. 1/2 rho V1 squared. And now I've moved 1/2 rho V2 over there as well. So he's minus 1/2 rho V2 squared. And so now that's my equation. It's exactly the same. It's still Bernoulli's equation. It's just I've rearranged the terms. I've moved them around. One side of the equation, the thing I'm solving for, is the difference in pressure, P2 minus P1. The other side is everything else. Once I have this, all I have to do is plug all my numbers in. But before I do it, let me make sure I know what all the numbers are. Because if I don't know all the numbers, I'm going to have to do some extra calculations first to get the numbers. So rho, I know rho, that's just the density. I'm talking about water, right? Water flowing through it. And I know density of water is 1,000. So I know that number. G, of course, is 9.8. H1. Well, do I know H1 and H2? I'm told that wherever the pipe was initially, it rises up by 30 meters. And I'm going to use the little trick that the lowest part of my pipe system is always going to be called the 0 point. So down here, the low part, I'll call H1 is 0. And the high part, I'll call H2 is 30 meters above it, which is 30. So H1 is going to be 0 and H2 will be 30. Well, that means, of course, rho GH1 being 0, I could just cancel him out. He's just 0. I don't need anything for him. H2, though, I now know is 30. So I know this term. This term is good. Next term, 1/2 rho V1 squared. Well, rho, that's 1,000. I know that. V1, do I know V1? Well, yeah. V1 is given in the problem. It's the speed of the water at the beginning, which is 5 meters per second. So I know that term. He's good. Last term, 1/2 rho V2 squared. Again, rho is 1,000, so I know him. Do I know V2? Well, no, I don't know the value of V2. I don't know how fast the fluid is moving at the end of the pipe. So this is something I have to calculate. And so I'll go ahead and work on that before I try to do anything with Bernoulli. I say, I need V2. Let's do it. How do I get the speed of a fluid when the pipe changes size? This is the continuity equation. Continuity says A1 V1 is A2 V2. The size of the pipe times its speed is constant. That is the volume flow rate. How much water flows per second through a pipe system is constant no matter where you look in the pipe. So I want to solve this for V2. That's the thing I'm looking for. So V2 will be A1 over A2 times V1. Well, what is A? A, of course, is the area of the pipe. And when we say the area of the pipe, we mean the cross-sectional area, as if you slice the pipe and you're looking at the face. It's a circle. And so the area is pi times radius 1 squared divided by pi times radius 2 squared. That's A1 over A2 times V1, which of course is V1. So that's what I need. All I need to do is plug these numbers in. The pi's cancel out and I have R1, which I know is 0.5. So 0.5 squared over R2, which is 0.1 squared times V1, which is 5. So 0.5 squared over 0.1 squared times 5. And I'm told this is 125 meters per second. Now, of course, before I use it, let me quickly make sure it makes sense, that there's not something really wrong going on. How do I do that? I ask myself the question, what do I expect? Do I expect the speed of the water to go down, or do I expect it to go up? And of course, the rule is if you constrict the pipe, the speed goes up. If you expand the pipe, the speed goes down. In this case, the pipe constricted, and so I expect the new speed to be bigger than the old speed. And that's exactly what I get. The old speed was 5, the new speed is 125. It definitely sped up because I constricted the pipe. So perfect, there we go. Now I know V2. So now I know all the numbers that I need to plug into this equation, and so I can actually work out the problem. P2 minus P1 equals. The first term was 0 because height 1 is 0 by my definition. Then we have minus 1,000 times 9.8 times H2, which is 30, plus 1/2 times 1,000 times V1 squared, which is 5 squared, minus 1/2 times 1,000 times V2 squared, which is 125. And there we go. All the numbers are plugged in. So all I have to do is get them in my calculator and I'll have my answer. So we have 5 squared minus 125 squared times 500 minus 1000 times 9.8 times 30. And I get an answer which is minus 8094000 pascals, which, if you want in scientific notation, is minus 8.09 times 10 to the 123.456 pascals. And there we go. What the number happens to be negative. So if I'm an engineer, what does that tell me? The negative pressure here tells me the difference in pressure is negative, which means I expect the pressure at the top of this pipe system to be this amount less than the pressure at the beginning. Why might this be important? Well, let's say I'm designing an apartment building and I want to make sure that all the showers and all the different floors have good water pressure so the tenants aren't aggravated. And so I say, well, if I go up to this top floor, which is 30 meters above the bottom floor, and the pressure is this much less than the starting pressure, then I better make sure the starting pressure is big enough to allow the type of water pressure I want at the top. So I want there to be enough pressure at the top to make a good shower. So I better have the pump at the bottom floor be strong enough, P1 is big enough to overcome this change in pressure. Okay? That's one way of thinking about how this type of calculation could be important. You're literally designing a system. You know what the system has to do. So maybe you say, okay, well, this is a big, big drop in pressure. So maybe what I should do is have, change the sizes of these pipes in some way. I know I have to go 30 meters up. So maybe if my original pipe wasn't 50 centimeters in radius, maybe if it was only 20 centimeters in radius, it wouldn't be such a big pressure drop. Or maybe it needs to be even bigger of a pipe initially. I don't know. I'd have to do these calculations to see. But that's basically what an engineer would do, or at least an engineer that would do calculations rather than drafting. They do these types of calculations. They say, okay, what do I want? I need there to be a pressure difference of blah, blah, blah. So what type of pipes should I use to get this type of thing? Because my pump can put out a pressure of this. So I need to make sure that the difference in pressure at the end of the day is less than that. And you go from there. But anyway, for this particular example, are there any questions? I think probably one of the biggest takeaways, other than generally speaking how to solve this problem, is the fact that we did not use at all this piece of information, and we did not use this piece of information. The fact that the pipe was this long, it went that far before it bent upwards, is completely meaningless. And same thing up here. I don't care how far the pipe went straight before bending upwards. That doesn't come into play at all. So when you're reading a problem on a test, if you see that piece of data sitting there, it's tempting to want to have to use all the numbers that are in a problem. Because if they're not important, why in the heck were they given in the problem? Well, that's the thing, because in real life, when you're working with an actual issue, an actual problem, you have a whole bunch of data, hopefully, and you don't know what's important and what's not important. Here's all the stuff I know. This is how the pipe system is. You, however, being the expert, know that the only things you really care about is what's the size of the pipe and how high or low does the pipe go. That's it. The size of the pipe tells you about the velocity. How high or low is the rho GH term. So all the other information we happen to know about this pipe system is completely unimportant. And don't be tricked by the fact that it's sitting there as a number for you to use. And so you think, oh my God, I have to use it somewhere. Where should it go? It doesn't matter. You, being the brain doing this calculation, you have to be able to tell, when given a problem, what pieces of data are important for you and which pieces are not important. And you ignore the not important stuff and you keep the stuff that you need. That's why I wanted to do this example, to make sure you see that sometimes you're given problems with extra information and you just need to be okay with it. You say, well, the fact that this pipe ran along for 20 meters, who cares? It could have ran along for 200 meters. It doesn't change anything. Of course, in the actual real world, it would change stuff because you have friction as you try to send water through pipes. And so the longer the pipe, the more drag you're going to feel. And so the initial pressure has to be bigger to overcome these losses. But we're doing theoretical world right now. We're just introducing the topic. So the fact that the pipe is this long doesn't matter. What does matter is how big it is, what the size of the opening is, because that goes to the velocity of the fluid. But how long it is, who cares? So don't be afraid to ignore information if it's not needed. So this particular example is the most complicated version of a Bernoulli problem I can give you. It has everything in it. It has changes in height. It has changes in velocity. It has information you don't need. It has all the terms that you have to keep track of, and you have to use continuity equation. All of that in one big example. So if you can go home, tomorrow or the next day, and you have a blank sheet of paper and you read this question without looking at the answers, and you could work this out, then any question on the test I give you about Bernoulli should be a piece of cake, because it'll be at this level or less. Maybe I give you a problem on the test where it doesn't change height. It only constricts. Well, all the height terms drop out. That's less stuff you have to worry about. Or I give you one that does change height, but it doesn't constrict. It doesn't change size. So all the terms with velocity you can ignore. You don't have to do continuity anymore. Anyway, any questions about this fluid stuff? All right, so as I said at the beginning, in case you were a little late to the class, we're now finished with fluids. We were going to get into a second half, being Archimedes' principle and buoyant force and things like that. But because we're getting towards the end of the semester, we basically have 1 month left. I want to be able to get to the last topic with enough time to go through it pretty good, which will be light and optics. So next class, we'll do an exam review, and we'll have our exam on fluids on Tuesday, next Tuesday. So Thursday, this coming Thursday, I'll come in as we did last time for the exam review, go over the topics. What did we discuss? These are the equations, and then give you a chance to ask me questions. If you want me to work any particular examples out, I'll be happy to. Tuesday of next week is the test, posted on Canvas like last time. Download it, work it all out, and then submit it back by the end of the night. And then next week after the test is when we'll start optics. Optics will be our last topic for the semester. Do as much as we can, have a test on optics, then we'll have a final exam review, and then, of course, the final exam. So that's the roadmap for the rest of the semester. So that's all I have for today. If you've got no questions, of course, you are free to go and enjoy the rest of your day. I will see you on Thursday.